Hi guys, I'm Eric Nordmark. I'm the chief architect, and I think we have Roman with us as well.
Yes, we do.
Okay, so feel free to ask questions as we go along. We've had some of this architectural material on the LF Edge page for a while, like a couple of years, but this is an update based on more recent work. So, comments, clarifications, everything is fair game. There are actually a couple of slides in here which we probably won't upload, but they'll be part of the recording that actually talks about some Solida specific perspectives in this space as well, which we thought would be useful for context. And one of the things, I think that you might have varying degrees of sort of knowledge about what is in Eve. So if it's too slow or too fast, you've already heard it, feel free to yell that this stuff is known. So this is actually the agenda that Vijay had shared earlier, right? We have a couple of things for this session, and then there's 2 more sessions that are planned right now. So there's about Eve and how it fits in, and its security and sort of the main components of it. So let's start with the Edge, Eve, and LF Edge. So some of the things that people realized, this setting context, right, was that as part of LF Edge, it wasn't clear what Edge meant, and people were working on telco-focused ones and different things, right, regional data centers, whatever, all the way down to microcontrollers and whatnot. So there's actually as a document, its URL is down at the bottom, right? This publication download thing, and oh, why does that pop up on the end of the screen when I share? That's a bit annoying. Basically looking at what are the different characteristics across different parts of the Edge, and the place where we play with Eve is this thing that they named the Smart Device Edge and the on-prem data center. It's basically things that are out inside the enterprises, but it's not microcontrollers just interacting with one sensor, some actuators or whatever. But it's also not, things inside the service provider network or at their edge. So things that are capable of running applications and have some headroom to deploy different applications, right? Not things that are built with only one purpose in mind. And then there's actually an animation in this thing. So some of the challenges at this user edge, right, is a large diversity, both of the actual hardware and the gateways, or whatever you call them, servers, and the applications. So this requires, infrastructure management, as well as the orchestration or management of the applications. And we can have, some applications that make cloud assumptions, meaning that, the infrastructure is there managed by Azure, AWS, Google, whatever, and I only worry about my apps. And, that might not be what it looks like out at the edge, because it's basically running on, bare metal hardware potentially. The other thing that shows up is, a need for scale and automation, because this is a lot more geographically dispersed than, the typical large-scale deployments inside data centers. So, in a large data center, someone might be going around with, on some scooter, changing things or repairing things that need to be, resetting things. You don't have that out at the edge because of the geographic distribution. So this means that the whole sort of initial deployment at scale, how do you make that as painless as possible, as well as the ongoing maintenance. And we also see more of the longer life cycle out here comparing to data centers and cloud infrastructure, which actually makes a difference in terms of what type of things do you need to be prepared for during the life cycle. Security is also different. The threat vectors are different than what you see in different environments. In a data center, you have, or in the cloud, you have some network security, you have some physical security, or very strict physical security. So that's one thing that differs. And if you're coming from an embedded compute environment where you have things that are not connected to the internet, well, now you're connecting them, right, as part of this. So it's actually different than what you're used to in the embedded environment as well. you can have varying requirements. The actual concerns from IT sort of network security and operational sort of, what does it mean from a safety perspective if things stop because there's some security alarms, right? It requires some care in that space to make sure that it actually hits the right balance. And last but not least, the connectivity inside a typical data center, it's all Ethernet, right? Well, here we have diversity in terms of connectivity, networking, and I/O, serial ports, LTE, Wi-Fi, various radio protocols, basically dealing with just at the physical layer of connectivity, not about all of the protocols you might run, but just the physical connectivity. It's actually very diverse. Right? And the last point is that in some cases, the entity deploying the equipment, they might not know much about and not control and not fully trust the enterprise IT that runs the network in which this thing is connected, right? So IT might not trust the box that gets deployed or the software that gets deployed, but it could be that the trust isn't there in the other direction either, right? In terms of, do I trust the patient data in my hospital to the IT administrator? Well, maybe not, right? That's governed by other things like HIPAA and whatever. An example where these things actually are different. And when we look at how do people, again, giving some context, where do we think that people, sweet spots for sort of deploying this in sort of industrial IoT settings, right? Is that one part is, where people want to deploy things to do various, network segmentation and proxy, and you want to be able to have control of that and being able to update applications and have some handle on security. The other one is, deploying very software appliances that basically do protocol inspection that can happen down in, the OT network where, people might look at Modbus traffic and whatever to look for potential issues, right? Traffic, security, whatever. And another place where it's common is basically providing some workload consolidation for compute, providing a place where you can go and deploy different application workloads, doing analytics, doing AI, etc., right? Which can actually be in different parts of the network, and some of them even on the IT side of the house. So oops, oh wait, I had this thing as well. So I mean, as we will see, part of this is about open source, but there's other aspects that are open here as well. It's also about workload consolidation. Sorry, it's also about the partner ecosystem being open, right? And the basically trying to bring in as many players into this as possible to make the industry as a whole and the community as a whole actually grow. So that's why Solida as a company has a bunch of different partners, as we will see on the open source side of things. There are also a number of partners. So when we look at the open source side of things, so LF Edge is a foundation inside the Linux Foundation. And there are several projects in here that are addressing different parts of the edge. So, you might see that Eve is this little thing down in the corner. Well, but this is actually all about the user edge and enterprise. Other projects here focus more like Fledge and EdgeX Foundry are projects. They focus more about the data transformation and protocol interoperability side of things as people go deploy things in different environments. And there's projects like Home Edge, towards the residential side of things, like Reno, towards the telco side of things, and sort of more projects coming in as well. But the purpose of LF Edge is sort of making this whole ecosystem actually grow and make these pieces actually fit together so that they actually complement each other, right? Still having their own unique benefits. And then interacting with other open source communities, as well as other, standardizations and consortia. So that's gives you an overview of what all is happening in LF Edge, and we're in many cases we are LF Edge as a whole is showcasing solutions that actually use Project Eve as one of the underpinnings for deploying Fudge, for deploying EdgeX Foundry, etc. And creating a blueprint using Eve as part of it. So showing how it works together. And so here at the top we have the setup projects, right? I said I created on EdgeX Foundry. These projects started a bit before us, before Eve, and in the impact stage, and then we have Eve, Fudge, Home Edge, and this other document effort called State of the Edge, which is in growth stage, and there's new things coming in on the left side here, Beetle, Open Horizon, and secure device onboarding. And there's a large number of members of this. This is just the premier members in LF Edge, but basically a significant chunk of industries actually participating in this in various forms. So any questions about this sort of introduction and LF Edge? So if not, I can continue on with Eve, and what is Eve really, right? And if you take it apart at the highest level, we see this thing saying, okay, you have something that is Eve here running on some edge compute hardware, and it uses some hypervisor. There's different hypervisors, but it's fundamentally providing this orchestration of what the things that actually get deployed on the device. And as such, it has several Eve services to do this. It implies some amount of overhead to go deploy this in terms of memory and disk and CPU. But then you can actually deploy different things. So you can actually deploy, K3OS, you can deploy legacy Windows or Linux workloads, you can deploy Docker containers, right, or OCI containers, and manage that both from a lifecycle management, security, whatever, number of different things. And when you look at how does this stuff actually fit in, right? Eve is not a standalone thing. It actually, its benefits in terms of scale and management is done by having it always use a controller of some sort. And there's two ecosystems of controllers using the same standard API. So we have Eve here on there. When I move the mouse, you can actually see it. So we have Eve here running on some hardware, deploying some set of applications. And then that talks to some controller over an open source API here. And that controller can either be, the Sedida commercial controller, which comes with an app marketplace, a web console, etc., or it could actually be something that is part of LF Edge as well, or part of the Eve project, which is a controller called Atom, and a driver that can basically be used to provision Atom, which is called Eden. Right. This is mostly used for testing setups to enable us to run our CI/CD pipeline, for instance. But it's one of the alternatives in this thing. And it could be that there could be other controllers that can actually come in, right? This API is open. It can actually be configured to talk to anything. And then at the other end, yes, Eve is the key thing from LF Edge here. Runs on different hardware, can deploy VMs or containers. And those VMs and containers, they can connect to any cloud, right? And you can have local things like Historian, SCADA, on-prem systems. We're not trying to constrain this. We're not compromising on security. The system has been built from ground up to support hardware root of trust and sort of security built around and on top of that. So using trusted platform modules and providing VTPMs to the applications. Oops, I thought that was another part of the animation, but that's part of the sort of pieces of how this stuff actually fits in.
Eric, a quick question. You mentioned that you're using the open source, the Atom controller for your CI/CD pipeline. So in scenarios where, let's say, we had a full integration need, right, for Eve and Zeta, would we use that, or could we still, use the commercial offering?
No, I mean, yeah, go ahead, Roman, were you going to answer?
Yeah, no, I was just going because, I just based on my experience, I don't think there are many cases where you guys would use Atom unless you would like to join our community as developers. So if there's anybody in your organization who would like to just, be a bona fide Eve developer, right, help us, create new features, fix bugs. We do have customers who also become our partners that way, so it's not uncommon. If you have anybody like that, then yes, you would use Atom. If you are a straight up customer, I really don't see any scenarios where Atom would be useful for you.
Okay, so in cases that, let's say we needed to do from source code all the way to deployment, we wanted to basically have a scenario where we built images and pushed it as part of our CI/CD pipeline, we could still use the commercial offering. We don't need to go down and use the open source.
Well,
yeah,
that's,
Go ahead.
Oh, okay. Yeah, that's a good question, because I think, what we also probably need to discuss is, sort of the difference between what's cooking in the open source and, what's commercially supported in terms of Eve, right? Because it doesn't mean that everything that you build off of the source will be supported by the commercial controller. Let me put it this way. So when you say that, when you're working with source code, that automatically, in my mind, puts you in a category of a developer, straight up developer. And at that point, commercial controller may not even be compatible with what you're building.
Actually, the question was slightly different. If we need, when I talked of source code, I meant if we're developing our apps and wanted to have that as part of
for that, you will work with the controller, the Zedera controller.
With the commercial controller, yeah.
Yeah. So the CI/CD pipeline will directly use the apps from APIs from the commercial controller.
Yeah, and I mean, we're using, from the CI/CD perspective, right? We're using Atom and Eden to ensure that Eve gets well tested and that the API gets well tested to Eve, right? Where it's not a useful way for you to test the applications you deploy, right? You would do that with your own application testing in your own CI/CD pipeline. And in general, the CDI controller is a lot more feature rich, right? And is built to be scalable. The cases when you would actually want to use Atom is more like, yeah, I know that I'm only controlling today. The way it's used, it's controlling one device, right? One instance of Eve for one instance of Atom. It might change over time depending on what the community wants, but that's sufficient for doing what we're doing today. So. That's a good question. So, and the other thing, again, to some context, right? When people think of this, I mean, you guys have been in this game for a while, but when we talk to people that are coming newer to edge computing, they say, well, I can just spin up, it was Docker last year, Kubernetes, whatever, at the edge, and, what else do I need, right? Well, that's just about running the actual apps, but the actual underlying support infrastructure you need to do that, from monitoring, from security, from connectivity, right? Running on different hardware, providing the right abstractions. It's actually a fair bit of things that are needed there to make this stuff work well. So in general, right? I mean, I think you probably are past this thing, but in general, where we see people starting to think about something like Eve making sense is when people already have figured out, okay, I have an application, might be a VM, might be a container. I've worked out how this stuff is, the app is functioning, right? And I deployed it in 10 places and figured out the connectivity to the cloud, but now I need to deploy it at a larger scale, and I need to be able to operate it at scale over, a longer time period, right? Years, whatever, and need to worry about patching, updating, etc. How will this stuff all work? it also shows up when people have a mixture of legacy applications that can run as Windows, and new ones when the new ones are containers or Kubernetes clusters, and that's what you want to run. And people that are just coming saying, hey, we want to run some containers, but we don't know what security will look like for the substrate, right? Hardware root trust, firewalls, VPN integration, how to actually get out security updates for the container runtime and underlying OS, right? And the fourth one is people that see, yeah, I have something, but I need a bit richer connectivity, right? Can you guys help with this? And those are the places when insertion points for sort of existing work underway where Eve fits in. So in terms of, sort of what are the key things that we provide as part of this architecture? Well, it starts, actually it doesn't start here, but a key thing is, thinking about the install, it actually starts in the factory, which is on a separate slide, but the key thing is actually making it easier from the beginning of time. So zero touch is about enabling drop shipping to the installer, where the factory can actually install Eve and deal with or extract device identities. And the installer is just someone that gets on a ladder or cherry picker or whatever, right? Physically installs the thing, powers it up, and verifies that it actually connects up to the controller in the cloud. So one of the little corners here is that, yeah, getting some visual feedback to the installer to say, yeah, correctly connected, meaning that the Ethernet cable was plugged in, etc., right? There was no enterprise firewall that prevented this stuff from connecting. And once you've gotten past that point, everything else can be done from the cloud, from the controller. The actual edge containers, the applications that you deploy, as well as the device lifecycle, changing the connectivity and patching and updating. And we've spent a lot of time to actually build Eve in a way where that those changes doesn't actually turn the device into a brick, meaning that it can no longer communicate. It's just sitting there consuming power, and you cannot reach it to manage it. So the idea is that only when the hardware is broken and needs to be fixed or replaced, or you need to do some cabling changes on site, those are the only times when you actually need to go physically visit the device. So the other thing that's key for Eve is being able to handle any edge nodes, right? Any type of silicon, any type of box, and from different vendors, basically saying that this can actually be common, so that you don't need to have vendor-specific management solutions and operational solutions. And this is, as we touched on before, done with the controller. The user interacts with the controller to specify configuration. The actual device calls home to get its configuration, to get any updates, as well as reporting its status. And with a rich set of silicon. So did I have a slide here? Yeah. So if you drill down into more details, right? Eve today supports both ARM as well as the Intel AMD processors. And we actually want processors to have support for hardware virtualization, since we leverage a hypervisor for strong isolation underneath. But this is quite common even in low-end processors in these families. And it supports a large range of upstream as well as downstream connectivity. And if it's actually supported by Linux, it's actually easy to add to Eve, right? That's a place where the community can contribute by saying, okay, we need to support these device drivers. The device drivers exist in Linux. Okay, just bring them into Eve. As well as supporting different downstream I/O, serial ports, USB, audio, etc. It's also a place where we see people from the community contributing, saying, hey, there's these additional connectivity options. How do we plug them in? How do we virtualize them, ensure that they're actually secure enough. And I think I touched upon this. I mean, in terms of what it can run, it's both positioned that from a open source perspective, we're running things like EdgeX Foundry and Fledge, but we're also running commercial things, edge runtimes like a Sorority Edge, AWS, Greengrass cores, etc. And the key thing for this, enabling this any application, is that the applications shouldn't have to worry about, do I need to have an LTE variant and a Wi-Fi and an Ethernet variant? No, right? The applications, they see virtualized connectivity where they don't actually have to worry about those differences, other than the performance characteristics. A key thing at the edge, as I touched upon earlier, is what are the security threats that are there? And at some level, this is the confluence of what you see in the data center, what you see on your phone, and whatever. It's a range of things. At least in the commercial sort of IoT space, user access has been a problem and still is a problem, that people have usernames to access their lawn sprinkler controller or whatever, right? Or there are other devices in the house, which is a potential problem. But we also have physical access, plugging in USB sticks. If people can go up and clone or steal part of the device, right? The network, right? This is not new. It's not unique to this, but the fact that you could actually try to DDoS the devices, distributed denial of service attacks, or try to attack them to break in, to exploit any bugs in the applications. And then, once you're inside, well, this device could also become part of a botnet attacking others. We've seen this with, people doing it with servers and desktops and whatever, and also doing it with consumer IoT devices where you attack the DNS, etc. So you need to think fairly holistically about the set of things that appear out at the edge. So what we've done in positioning this stuff as Eve is something that we call zero trust, and sort of looking at both people, processes, and technology. So the key thing on the people side is saying, we don't actually need usernames and passwords to handle these devices, because the users actually talk to a controller, and the device has a strong security relationship with the controller. So, role-based access control, etc., happens in the controller, where, it's a lot easier to do this using standard, sort of state-of-the-art for web services. On the process side, the key thing for us is to be able to handle, 7+ years of lifetime at the edge. And when people deploy things in data centers or the cloud, they might say, well, we're replacing this hardware every 2 or 3 years. We might not have to worry about patching everything, right? We can sort of get away with, or they might think that they can get away with not having solid patch infrastructure. 7 years, the number of security relevant bugs that will come up in some software that you leverage, that is clearly something you have to be concerned about. The other one is, being able to figure out how to observe what's going on from a process perspective. And here, Eve enables you to do that by the Eve API providing sufficient information in terms of resource usage, firewall violations, so that you can actually build analytics elsewhere to see, okay, are there differences between different parts of my infrastructure? If 2 of my devices suddenly start seeing some firewall rule violations, but my other 998 do not, right? I should probably look more closely at what's happening on those 2 devices. Finally, in terms of the technologies, right? We're using standard components for doing this to build a solution which actually is state of the art, but it's things like hardware root of trust, leveraging trusted platform modules. Crypto-based IDs. Instead of having usernames and passwords, we have identifiers based off of X509 certificates, and using measured boot and remote attestation. And we've worked with you guys to put some of that in place. Encryption at rest and in flight, with standard TLS, and the keys being sealed by the TPM, the standard sort of TPM feature that we're leveraging. We're doing signed images for both the Eve OS as well as for the applications, leveraging hypervisors for strong isolation and defense in depth. We have a distributed firewall. You set it up from the controller as part of deploying applications, and it ensures that, or it pushes you in a direction where you say, I should actually think about what my app needs to talk to, who it needs to talk to. We have physical security, being able to do port isolation and turning off sort of physical ports on the box. If you're not using the USB ports, but they're there, well, there's no software there's no device driver that actually reacts to anything being plugged into that port. And as well as sort of at a higher level saying, okay, Eve can run applications. One of the applications it can run are security appliances that you actually deploy on Eve to actually go and observe traffic, whether it's on the network as a whole or whether it's observing traffic to and from the applications being deployed on that instance of Eve on that device. Any questions so far? Someone is still there. I'm not talking to myself, I hope.
Okay.
Yes, we are.
They're still here.
Okay. And one of the disadvantages of this, remote presentation, but as opposed to being in a physical room.
Yeah.
So on the architecture front, so in terms of drilling down into what is actually all inside Eve, right? So this is not about the features it's providing; it's more about how are these things actually provided. So I'll get rid of these green things, but in a little bit. But what people traditionally think about when they talk about having a runtime is that you have some application instances. We're calling them edge containers in the Eve project, and we have some runtime for running that stuff, right? And that's sufficient, right? But when we talk about these other challenges out at the edge, well, there's a couple of more components that we need. So if we start down on the left side here, we need some sort of fundamental security that ties into this, that can handle onboarding and identity, etc. As I said, to patch things, well, it's not sufficient to be able to enable updating the applications, but we also need to be able to update Eve itself, all of its components. So there's a self-update thing here and making that stuff be robust. Eve needs to be able to connect to the controller, and this is critical because if the promise is that we don't have to visit the device unless the hardware is broken, or you need to recable it. Well, we shouldn't be able to configure the device in some mode where it somehow no longer can talk to the controller, right? Because then we don't deliver on that promise. So connectivity there is key. The APIs, this is the way we manage things. Well, the APIs need to actually be secure, right? And function in the sort of network environment where not only is there diversity in terms of the technology used to connect, but this thing might be mounted on a truck and the truck drives through a tunnel. Well, when it comes out of the tunnel and gets LTE connectivity again, well, things should carry on, right? As opposed to you getting intermittent failures because you're outside of range for a bit. So the structure of that API to handle that type of connectivity is actually key thing. And then sort of the applications, right? Yeah, the applications need access to richer connectivity than you typically have in the cloud. So we'll drill down in that as well. So if we open this stuff up, we can see that, yeah, there's the various security features over here. These things are by and large separated as separate microservices inside EVE itself. So the idea and the architecture is that you should be able to have some defense in depth, so that the things that actually verify the signatures are very far away from the things that actually interact on the network. So if there is a bug somewhere in the TCP/IP stack or in the TLS library that we use, right, that the verification of the signatures should be isolated from that, so that you can actually detect things or limit the impact of any sort of security breaches because of software bugs. And trust me, based on history, there will be security relevant bugs in the various packages and libraries that are being used in any software, right? So you need to be able to prepare for that. And then we will talk more about this thing in terms of the services provided to the applications, but it's fairly richer in terms of the set of different connectivity that we can offer. So I will drill down into those things. So if we start sort of based from the life of the device, right? One of the first things that happen with a device when it gets deployed is that it needs to be onboarded to the controller. And as much as possible, you want to sort of front load this and have the factory do this, right? But what the factory can and cannot do might depend on the actual manufacturer of the hardware. They might be able to pre-install EVE, but they might be able to do other things as well that help with the identity part of the puzzle. And if they're not doing that in the factory itself, it's something that gets done as part of some staging, or you loosen up your security requirements for the initial onboarding a bit. But fundamentally, the notion is that the device identity is generated in the trusted platform module, and the private key never leaves the TPM. This ensures that you can never clone a device, right? Because its identity is in the TPM. And the device is also imprinted, right? Told what controller to trust, which is in the form of a root certificate authority certificate. So anything that is, it doesn't have to be, CDDOS, it can be anything that people want. This is an open source project, right? So different players might deploy devices trusting different controllers or controller infrastructure. And then in the factory, or when you do this, when you install EVE, you might have different processes to extract these identities. And the most secure one is to boot the device once, have it generate the device certificate, and then extract that device certificate onto a USB stick or over the network in your secure manufacturing facility, right? And then record that with the device. But in other cases, that's not possible, but you have a serial number. And you can take these things then and ship them together with the hardware. And those are later used when the user actually registers their hardware with the controller. But the other thing that can be done in the factory or in the staging step is you can pre-onboard the device, but you can also pre-install application software content. So if you know that all of these things is going to need these gigabytes of software, where you can actually do it once, or you can do it when it actually gets deployed out in the network, right? It's just sort of saving some bandwidth later. The registration, since it actually happens with different security properties, depending upon whether you're using serial numbers or something stronger, the controller actually, the protocol is done so that the controller can actually detect when there's a duplicate registration and says, wait, this doesn't make sense because somebody's already registered, right? If someone is guessing the serial number or stealing it or making a copy of the documentation that has the serial number on it, well, it will actually get detected. The stuff at the bottom is a link to the actual page in GitHub that talks about this part of the registration. So a fair bit of this is documented as part of the open source project. There's docs directories there. So when you actually go and power up Eve, right, on some hardware, the booting part of this stuff is key. So there's a wide diversity of hardware, and different hardware actually use different ways of booting things, and we're trying to support a reasonable set of these things, while at the same time ensuring that we can actually do this measured boot feature, which has dependencies on parts of the boot software and firmware change of things. But UEFI is the normal way of booting things on x86. It exists on some ARM boxes as well. You can do legacy PC BIOS boot, and there's support for core boot. And we support Raspberry. The open source project actually runs on Raspberry Pi 4s. So that uses a different U-boot firmware. And then as part of Eve, we have this thing to ensure that we don't brick the device when there's something bad going on. We have 2 partitions for booting, and that uses the GPT partition tables. And as part of this, as I hinted at, and we're performing measured boot, which is a standard procedure, but it's not supported uniformly across industry. And the mechanism for doing this is, or the way to sort of strike a balance between the operational needs and the sort of IT security needs, is that if some software has changed, software or firmware, in the BIOS, for instance, in that case, Eve requires a remote attestation handshake to the controller, to basically where the controller gets to say, yeah, that's a known version of Eve, that's a known version of the BIOS for this platform. Their measurements, which are these cryptographic checksums, right, all match. And then at that point in time, the controller will unlock the application disk. So basically, if you have any secrets on the application disks, a user can't come, or someone with physical access can't flash the BIOS and then run some other software that will enable them to actually read what was on those disks, right? That doesn't work because of this handshake. But if you just have a power outage or whatever, you just move the device, if you're getting this, you will get the same measurements. And in that case, Eve will actually unlock the disks, start the applications, because these keys are actually sealed under the measurement in the TPM. So this is explained in great detail in this link. And one of the things this will actually do is it will detect that, oh, you have some version of firmware, or you have some version of Eve that somebody else built at home and installed, and it's actually not something that's supported. It's not something that's known, hence we don't actually know whether that has some backdoors or whatever, right? So we'll actually flag that stuff and not let it proceed. So there's more on the booting details as well as that link. Any questions so far? So on the device connectivity side of things, so one of the services we have is called the Network Interface Manager. So its key job is to make sure that the device always has connectivity to the controller. This connectivity can be redundant, like I have both an Ethernet and I have an LTE connection. And that can be done in an active, if it is, it can be active-active or active standby, right? Only use LTE if you don't have connectivity on the Ethernet stuff. So it's some basic things to say that Eve will try hard to connect to the controller as hard as possible. The default behavior when you just take Eve out of the box is to try all Ethernet interfaces, and Ethernet here includes things that like Wi-Fi and LTE, provided that you don't need any additional credentials to access that network, and just run DHCP and get an IP address and reaching the controller. But there's environments where this isn't sufficient, so we can actually override this, which we do with either a USB key that you install in the device as part of booting it, or you plop in a USB key and then you configure it with this, or you can build it into the image if you want, or you can stage it in an environment where you have DHCP and then feed it from the controller. There are different ways of doing these sort of special networking requirements. But that's used so that you can actually specify static IP addresses if it's deployed in enterprise or in shop floor networks or whatever where you don't have DHCP servers. You can specify HTTP proxies if you need to access some proxy and maybe that proxy has some proxy certificate that needs to be trusted. You can specify those. If you need to specify, credentials for Wi-Fi connectivity, etc., right? Those are things that go into that specification. But once the device reaches the controller, then the controller will specify these parameters. So, in the normal case, it will tell the device exactly what it got from this USB stick. But you can then actually later change it from the controller, saying, "Hey, I need to use a different proxy, and here's the new proxy to use." All of those changes are verified by Eve before they're put into effect. Was there a question?
So far, and point number 3 here, it can be overridden with a file on a USB. So is that something, where does that happen? Can that be like, let's say out in the field, you ship the gateway, you ship the box out the field and then you want to change it there. Is that the way to change it, and that is the only way to change it?
Well, yeah, so there's a couple of different ways. Yeah, when it goes, if you need to install it, for instance, in an environment with static IP addresses, right? If you basically need to know, well, all of these boxes that get deployed, and the static IP addresses are different for different deployments, right? Then you need to say, well, I need to get this into the box somehow. Well, the box doesn't have a screen and a keyboard, so you can either as part of installing each box, you have a USB stick with the IP address of that box. And you put that in and you power on the device. And it picks it up and it then connects to the controller. And now, everything is fine. You now can manage it remotely. Or you can do it by staging things, which we have users of Eve actually do, where they say, okay, I'm bringing this stuff up in my environment. And there I have DHCP. But then once it's up talking on DHCP, they say, okay, this device is going to customer X, it needs IP address Y. Tell the device about that configuration. And then power it off, box it up, ship it to the customer. And then when it comes up with the customer, it already has that IP address. Right?
Yeah, but is that, most of the cases you will not know that, the second part.
Yeah, no, but sure. Which is, but the assumption here is that you don't have a user interface on these devices as they get deployed, right?
And Moin,
so you will create the USB stick when you go deploy it, and the customers can do this stuff. It's basically a text file to edit. Yeah.
Yep. Eric, I was just going to add that, like it's a USB stick which has a JSON file with the network properties. Think of the customer logging into a device. If there was a access to keyboard and monitor, like whatever they are going to type it into that thing, they are just going to put it onto the USB stick and then plug it in. and that works. So you need to bootstrap the device in one way or another. And if the information that is needed to bootstrap the device is only available at a customer premise, then like you can do that at a customer premise using
that one, you need to have the USB port enabled on those devices.
Correct. Yeah, and Eve actually managed that, right? It actually knows that. Well, I should. You will then actually turn it off afterwards. Right? So, but when it comes, I'm trying to remember the exact code, but I mean, you can ship them with the USB port actually disabled from the factory as well, or you can say keep this open so that if I need configuration, you'll actually go read it. So.
Okay.
Okay. But yeah, an important thing is this testing thing, right? Verifying things so that you don't, if you feed some bad parameters, that it actually does fall back to the old one and continue. So the next step, and this is not necessarily in time sequence, right? But because you would typically then go ahead and deploy some applications and whatever, and then some number of months later, you would say, oh, there's a new version of Eve here. I should actually go and deploy that. But a key thing in terms of managing the infrastructure is being able to update all of EVOS. So this includes the hypervisor, everything. And this stuff has been built so that it can actually handle any failures, short of the hardware, sort of breaking. But if the power goes out while it's writing to the disk or SSD or whatever, then that we deal with in Eve. And bad Eve images that means that you can actually be able to connect to the controller. And you would think that, well, but testing would cover that. But I think that as hardware manufacturers roll out variants of their hardware, I know that in some domains, they might not tell you that, oh, this thing has the same model number, but they actually changed one of the chips to a newer version or a cheaper one or whatever, right? And sure, all of the device drivers support that, right? Well, maybe in Windows they did, but so you don't actually know whether there will be something that comes up on one particular device or a subset of your devices that you put on Eve. It might not work the same way it worked when you tested it on the identical models before you did this. And plus, we've been using this stuff as part of our daily operation as we've been developing Eve over the last number of years, basically exercising this mechanism all the time, even with Eve images that are poorly tested to begin with, so they actually do fail. So we know that this is getting exercised all the time. So this is driven from the controller, right? The controller specifies what Eve image to use as part of the API. Eve does the actual download verification. It copies it to the other partition and then reboots. And then the bootloader here uses this priority thing that I mentioned earlier. But the key thing is that if there is any failure, it fails to boot, it times out. The kernel crashes, whatever, right? It switches back to the previous partition. And then when Eve is up and running, and it by default, it keeps on running for 10 minutes before actually committing to this new version. And that means used to verify that it can connect to the controller, that the remote at the station, getting the controller to sign off on the hashes of the new software complete, and that we don't have any internal Eve failures as part of this, like some agent actually crashing or something, and then we're committing to this new image. So this is extremely robust. I have occasionally made this stuff fail, but this is basically running untested images, right? But it is built so that we haven't seen any cases in production where we've had any issues. It might fall back because of something, right? And it falls back to the old image, and then you have to look at, okay, why did it do that? What failed? But none of them had been that it's just sitting there and you physically have to go visit the device to recover. So part of this initial or updating to Eve, but also the ongoing running of it is relying on watchdogs to be able to self-monitor and recover. So we're using hardware watchdog timers, which exists when they exist, right? And they exist in many of these sort of edge computing type devices, IoT gateways, etc. Something that's enabled in the BIOS. And this means that if something actually gets stuck, the hardware watchdog says, oh, something is not working, I will go reset the device and basically reboot. And you have an opportunity to try again. If this happens during the update of Eve, it will actually switch back to the previous version, the working version of Eve. But then there's also, as you know, we're using standard software watchdog that verifies that the various Eve services are there and are responsive. And if that software watchdog fires, we actually save away the information about where we got there, and then we actually reboot, and now we can actually diagnose that thing with the customer's help or the user's help to see what went wrong. Was there a question? And we've seen on somewhat flaky hardware that all of these pieces are actually not sufficient. I know that the Raspberry Pis that we have tested on, or actually, sorry, there were High-Keys, another ARM board. Their Wi-Fi would somehow lock up after a couple of days, a week. And, you know, not clear why, but if you want to get it back to a state where it can be remotely managed and diagnosed, well, we have a timer that says, if you can't talk to the controller for a long time, right? Well, maybe it's because of your network hardware and or device driver that's gotten itself stuck somewhere. And everything else is working fine, it's just that it can't talk on the network. So this by default, the Eve today is set to 1 week. One can actually configure it to be anything, right? Because it's not supposed to fire just because, you know, the truck is in the tunnel or whatever type thing. But when it actually is having some problems, and you can set it, we can set it to a lower timer as well. And then we've added some initial monitoring of the disk and SSD counters to sort of look at some health. There might be more things coming here. It depends a bit on what the community wants to do here in the space as well. Basically, do more monitoring of hardware diagnostics or hardware information.
So in terms of connectivity monitoring.
Yep.
So the connectivity, that's the default behavior that's listed here. So, but the device may not have connectivity for some legitimate reason as well. So even in that case, it's going to be doing reboot every once a week.
That's the default. Yeah, you can actually set it from the controller. You can set what the timer is, right? So, and you know, if you're gonna, you know, depending upon what your deployment is, right, you might have an idea about what that is. You might also have an idea from having, sort of well-behaved hardware, right? So the place where we've seen issues are on these inexpensive ARM boards that people use for development purposes, not sort of production-grade hardware, right? So you might be fine setting this stuff to infinite, basically disable it.
Mm-hmm. Okay.
Okay. So on the Eve APIs, so the basic assumption with the API is, being able to operate basically in any network environment. This means that you can have asymmetric connectivity. I can only connect out from the device towards the internet. So basically it's phoning home, right? The API is structured that way. And as I said, unpredictable connectivity, right? Well, that means in terms of the API that it operates using eventual consistency where you in the controller might say, I would like you to run with this configuration, with these applications, etc. Well, if the device can't connect for the next minute, the next week. Well, when it does connect, it will actually pick up that new configuration, and the device keeps on reporting what its current state, right? So you can actually tell the difference that it hasn't picked it up yet. The other thing we have there is basically compressible metrics that, we're sending a bunch of performance metrics, but if you're not connected for a day, well, Eve doesn't actually retain all of that because we don't know how much disks to use to store all of that. It's potentially unbounded. So instead the metrics basically give you an average over the time that you were not connected, to make sure that this stuff works well even if you have long outages of connectivity. The API has evolved over time to both support end-to-end security, as well as man-in-the-middle content inspecting proxies that some IT organizations might want to have to make sure that there's no information leakage, etc. So this is something that took a while to actually get in place, but it I think creates a very good balance in terms of being able to deal with the different concerns. It has different API endpoints for scalability. So the various things that we do, right, on the controller side can be split up, and it uses TLS 1.2 and 1.3 depending on what's on the server side, and this end-to-end object signing to make sure that even when the IT department wants to look at the payload, well, they can actually modify it. And any user secrets that get passed are in addition protected by end-to-end object encryption. So, for instance, if you have if your images that you use, your applications are sort of secret, proprietary, confidential, and you're keeping them on some data store for your enterprise, well, you have to tell Eve the credentials to go download those images. But that doesn't mean that the IT staff at the enterprise where this is deployed should be able to see those credentials. But they want to be able to see the payload to do content inspection to look for information leakage or other things, right? So those things and other potential sort of secrets, they actually have an additional layer of encryption. I think I picked a picture. If that was too much to unpack, here's trying to depict this, right? In its most complex form. There clearly are simpler things, but if you start on the left here, we have inside some enterprise, we have a box running Eve, and it uses TLS, right? And this protects against any sort of network attacks trying to modify or read that data inside the enterprise. But then the user of this network, this enterprise, or the IT department for this enterprise has said, well, we need to do content inspection. We have a proxy. Here's the configuration. The operator of this device basically has configured that through the UI in the controller, saying, here's a proxy certificate that you need to trust in this particular deployment. It's basically the certificate that corresponds to the proxy running here. So this proxy can now basically decrypt this stuff. It can actually look at things inside, and then it will actually run TLS back to the actual controller out here. But the third thing, so basically there's TLS. So this TLS tunnel over here protects against, or TLS connection protects against any attacks out on the internet or whatever you might get them from, right? But then in addition, there's this signature that is actually on the object here, on the envelope, so that this proxy cannot modify anything. Any modifications will be detected and rejected. And the third thing is that this little teal colored thing inside the data that has your credentials for your data store or your cloud init with some secret keys or whatever, that is actually in addition encrypted between the different microservices in Eve and the microservices in the controller. So just to make sure that the operational data isn't or operational metadata, right, that is used for these applications isn't actually compromised anymore. Is that all clear? It's a bit complex, but the environment is a bit complex out there. So I think this is a bit detail about the actual API standard sort of RESTful API structure using protobufs for encoding. And the API is documented together with everything else. In terms of the runtime for the application, we've made Eve sort of be independent, right? It has a concept of tasks that provides an abstraction over the different container and virtual machine runtimes. We're starting to use KVM, the KVM hypervisor by default. We've been using Sen for a while, Sen as well as the Intel Acorn hypervisor work as well. And the project is open to bringing in other hypervisors. You'll find that type 1 hypervisors have slightly smaller attack surface, but different people might have different trade-offs in terms of what they want out of their hypervisor versus security. Eve as a project has the ability to run OCI containers directly without a hypervisor. I don't think it's something that's used in production yet, but basically, weaker security, weaker isolation, but might get other benefits out of it. Eve also abstracts the various resource assignments, as well as usage metrics that come out of the hypervisor. So this can be reported to the user through the controller in a uniform way. And we abstract this IO assignment pieces where we do IO pass-through of various sorts for networking, PCI, etc. And that is leveraging the different hypervisors tool chain to do that setup. So it's basically making sure that Eve is not wedded to only one task runtime, but is something that can evolve over time. So in terms of the storage that the applications need, right? Not Eve itself, but for the applications. It's structured as four, in essence, 4 layers, whether you consider all of them being part of the storage itself. But we first have this notion of a data store where you in the controller specify where Eve should go get images from. It could be your own local HTTP server or Docker thing. It could be your own S3. It could be something that's shared, right? You could, if you're deploying Ubuntu, you can just go and grab it correctly from Canonical. You just specify which image server you're getting this thing from, right? Specifying that metadata. And then the next layer is Eve being told about what we call content tree, which is generalizing the OCI description, the thing that you have in Docker containers, etc., where you have layers, right? And which fits in well with container deployment, but we are using it for VM images as well, that we're describing them using that structure. So this is now we're getting a bunch of immutable read-only content down to Eve, and then from that we end up creating volumes which are read-only or read-write, which is actually the virtual disks for the application. So the directories in which the containers will actually run as their file system content. And then the fourth layer is that when you deploy applications, you will mount the volumes that the application is specified to use. So in this picture, the controller provides the metadata, right? And the metadata includes the SHA values for these images. So even if you're getting the content from the Ubuntu update servers for an Ubuntu cloud image, you specify the actual SHA of that to the controller. So the Eve gets it through the API. That API is signed, so that if someone is spoofing you, the actual content, well, we're catching that in Eve as part of verifying the image. It also means that you can get these images, this content from anywhere, right? Because you always verify the SHAs of them once you have retrieved them. The other piece that I didn't put on this slide, I realized that as part of the security picture, that by default, these application volumes are encrypted, right? If you care about the last 10% of performance, well, of disk performance, you can actually specify that the volumes, the virtual disk that the applications use, should not actually be encrypted on the disk or SSD. So Eve has this notion, is capable of driving the update to the application images. And that uses or takes a make before break approach. So if you have a new version of an application, or in general a content tree, right? You tell the application, you tell the controller that I want to update this application to the new version. Well, you will actually, as part of that, you will first go and download and verify the new content. And once that is done, which could take a long time, right? And in the future, maybe someone wants to schedule that so it happens on Sunday night. I don't know, we don't have anything like that today, but the general notion is that the actual download and verification is actually independent of the application of this thing. But then once it has it, it will then actually switch and say, okay, stop the application using the old image, start it using the new one. So this is all running off of immutable content, which means that you end up recreating the volumes that you need, right? Which might be the volume that has your Linux root file system, but not your actual application data. But you structure things using multiple volumes normally. But it means that there's logic in Eve to do this make before break piece. And last but not least, right? I mean, in some cases you don't have a choice. You end up deploying huge Windows 10 images or whatever, right? Or Linux images. But if you have applications that you're building yourself, structuring them as OCI layers means that when you're shipping a new version of your application, well, it's not going to change all of the layers, meaning that the amount of data that needs to get downloaded potentially over some slow network, right, becomes less. So it's something to think about in terms of application development, that layers actually help here. So. Any questions so far? If not, we move along. Application connectivity. So, networking is a lot more complicated than I would like, but it's too many choices. But for some reason, we ended up with networking that way. And having worked on networking for 20 plus years, I don't quite understand why. But maybe storage is as complicated, but you don't see it. But in terms of the applications wanting to use the network, there's sort of this basic connectivity saying, this application needs to talk to the shop floor network on some Ethernet port, and whatever happens on the shop floor network, right? This is just some embedded thing. It's going to pick up Modbus over TCP or whatever out there, but maybe it's also running some protocol that isn't even TCP/IP, right? Some specific IoT protocols, whatever. Right? We have the option to provision networking for the application that way. It means that you're getting the ability to send and receive Ethernet packets, and you're just like if you were to plug in any bare metal box out there. The next one is saying, oh, I actually want some connectivity that's either entirely local to the host. Right? I have 3 different applications. They need to communicate between themselves, but they're running on the same box. Or there's maybe some local, but then you actually want to go outside, and going outside implies a NAT. And the third one is that, well, the application came from the cloud, for instance. It used to running in the cloud inside some VPC. And now, how do I deploy that thing at the edge? Well, this cloud connectivity is basically saying that you can extend the VPC that you have in your data center, in your own data center or in Azure or AWS, using a VPN where it's actually is Eve itself that provisions the VPN, so that the application doesn't need to change. It still gets the same IP address, and apart from sort of the performance, right, the latency, it looks like it's to the application as it's inside the data center or the cloud where it was before. So that's the cloud connectivity. All of these network connectivity options we have require firewall rules to be specified, because our sort of security approach is that, well, if you don't specify anything, it means that everything is denied. And sure, you can specify a rule that says accept anything, right? But at least you have to go do that specification. And then in addition to networking connectivity, there's different I/O connectivity. This includes assignments of complete I/O devices, which could be, network interface cards. It could be, audio, USB controllers, GPUs, whatever. Right? It's things that are typically visible as PCI devices on the PCI bus, and there's support for assigning serial ports. And this is important for applications that we see at the edge. One thing that is a bit complex in this picture, even though it's quite complete, is that you can actually do networking using an I/O device as well. Right? If you don't need to share your I/O device, your Ethernet card, right, your Ethernet NIC, controller, or whatever, then you can actually assign that whole I/O device to the application, and now it has full control. The application image has the controller, the driver for that card, etc. So it gives flexibility. But in other cases, you actually want to share things, and hence you use some of those 3 network connectivity options up on top. The other part that's sort of I've used part of the connectivity is, if you need to have console access, right, you can do that through various means. We have a remote console facility via the API through the controller, where you can, even though you have firewalls, NATs, whatever, you can actually go access this thing from your browser and get a console access, which is actually at least useful for testing things and debugging things when you have application issues. And then, the app connectivity isn't doing everything, right? But it's enough of a substrate to actually go and say, I can deploy additional networking functionality as applications on top of Eve, like SD-WAN, software-defined WAN, etc., which can serve things both running on Eve as well as running outside of the box on some other port. So we have a document that explains a bit about what these different models actually mean, right? There's some in terms of IP address management, where does DHCP run, etc. So, I have some examples of this, but if you have questions, you can, well, maybe I'll go through the examples first. See how we're doing on time. Have a few slides left. So an example that shows the different flavors of applications. This is all inside one device, right? I have 3 applications here, the things on top. I have this in this example. The SCADA application is some old thing that's not necessarily very well secured, but I want to be able to extract some data over that. The SCADA application was designed to basically speak Modbus on some factory floor network or whatever, and then have a feed where it can actually send off MQTT to somebody on some other network interface. And we go deploy that thing here, and we just specify some firewall rules saying that, just for extra safety, saying only allow inbound Modbus on this from this Ethernet here. And it's the physical Ethernet port. And then on the other port that the application sees, only allow MQTT TCP connections outbound. But then we wire this thing up saying, okay, we're deploying a local only network here, network instance for these applications to use. And this new analytics thing, we're specifying it to say, oh, you can only get MQTT inbound. And we have some local logger application in this example as well, saying you can only get MQTT inbound, meaning that these firewall rules here, they basically prevent, if there's any bug in this analytics thing, well, they still can't talk back to this SCADA box, that our SCADA application, which we don't know how well it handles network attacks. But then the analytics thing at the other end, right? It says, well, I'm going to feed this stuff back into my VPC sitting in the cloud somewhere. So in this case, it's been configured to say, and it does that over HTTP in this example. So it's been configured with a firewall rule saying only allow HTTPS outbound. And then Eve has been configured to say, yeah, for this particular network instance, here's the cloud VPN parameters to connect back out. And that connection happens over the Ethernet 0. And in this case, Eve itself is also using Ethernet 0 to go talk to the controller, right? So that shows you some of the power of these connectivity options, or the network connectivity options that we have in Eve. Any questions? So here's another one where we show how one can combine this to do a sort of high performance networking. So in this particular case, we have Eve running 2 separate applications, but it's fundamentally providing a virtual router for deployment, and it has some local storage if you want to deploy this stuff at some site, whatever, and manage it remotely using Eve. And like before, right? Eve is running management traffic that's using Ethernet 0 in this case, and the applications might be managed through some protocol, be it SSH or HTTPS or whatever, where you need to go configure what the applications are doing. So we've set this stuff up by having NAT here and having port map rules for the NATs. So you can actually, those protocols can actually go in and manage, through whatever management part of these applications on the storage service and on the virtual router. So that's sort of like, at some level, the control plane for this. Right? But then on the virtual router here, this thing might have some performance requirements, but it has, the box has some high-speed Ethernet ports, gigabit, 10 gigabit, even faster, just limited by hardware. And then those are set up to do this device pass-through, where the actual Ethernet drivers run inside the application and the kernel that that virtual router comes with. And then on top of that, you can run, DPDK, whatever, right? You have full access to those hardware devices. So not any different than running it on the bare metal from that perspective. But then you still have the ability of saying, well, I can have a virtual Ethernet driver here that talks over, a local only thing that allows the storage traffic can be routed over to the storage server. That's what this local only connection shows over there, right? So in this case, you get performance, but you get a strong degree of isolation. The only thing you don't have is, because this is device pass-through, there's no firewall rules possible on those. No firewall rules enforced by Eve itself, right? Possible on those ports, but that would typically be something that would be inside the virtual router itself. So I think that was it for the bulk of the content. Questions? Maybe I should not switch to the roadmap yet. But, well, I'll do that. A minute left, I think. So, the roadmap is something that's driven by the community, and where there's work going on some of these things, and some of them might be further down the road, but you can actually, well, the way open source works, the people that have the most influence on the roadmap are people that are actually writing the code as well. So, but it's something that is up to the community to decide. So there's some new Eve logging infrastructure, just making logging more robust and better performing, so that we can get efficiently get both logs from Eve itself for sort of monitoring and debugging, but also the application logs to various backends. We have pieces about getting GPS coordinates. If you have a cellular modem that has a GPS receiver, you can actually report those. There's some work underway there. We're using IP geolocation right now to show things on a map, making that stuff be more robust. Enabling deploying K3S workloads, including being able to share things in ways we haven't been able to do before in Eve when it comes to switch network instances. So this is to avoid having NATs when you don't actually want NATs, netted network connectivity. There's work underway to download Eve as OCI layers, so that we can actually apply layering there as well to reduce the size of Eve downloads, size of downloads of Eve updates in the future. And monitoring support for the application, so that we can provide even better information when something actually goes wrong, right? On a bare metal, you wouldn't see that at all unless you had a physical console or something plugged in, but here we can actually extract some things from outside of the application. Incremental image download, some volume size limits, this sort of storage pieces are likely to evolve to be able to get more flexibility on the storage side of things. And key takeaways: Eve is mature, secure, and then something else that rhymes, which I haven't figured out yet. At sort of a high level, the unique requirements at this edge, right, which is at some level the requirements you get for running things in the cloud, and then something about embedded, but then something that I think doesn't exist in either, right? The combination of them, it's actually bigger than the sum of the parts in terms of the requirements. To evolve things, you need to handle old as well as new, right? In most deployments, you have something that you're carrying with you. And networking is harder than you think, but the sort of, the hope with Eve as an open source project, LFEdge, is that you get an open source, open community, but also drive towards open ecosystems with partners, right? Whether the partners come from the open source world or if they're just leveraging open source to deploy their own applications, but become part of the overall ecosystem. So questions. I haven't been paying attention whether people have been writing questions, but
No, there haven't been any, Eric. So I think we are up for the time, and you guys have email address for both Eric and Roman, and or if any follow-up questions, please feel free to send us. We will glad to answer them or guide you guys to e-wiki pages. There is a lot more details available, detailed design descriptions. Hope this sets up the good context to read further. Thank you, Eric and Roman, for doing this.